Blowback is a system of operation for self-loading firearms that obtains energy from the motion of the cartridge case as it is pushed to the rear by expanding gas created by the ignition of the propellant charge. Several blowback systems exist within this broad principle of operation, each distinguished by the methods used to control bolt movement. In most actions that use blowback operation, the breech is not locked mechanically at the time of firing. The inertia of the bolt and recoil spring, S, relative to the weight of the bullet, delay opening of the breech until the bullet has left the barrel. A few locked breech designs use a form of blowback, example, primer actuation, to perform the unlocking function. The blowback principle may be considered a simplified form of gas operation, since the cartridge case behaves like a piston driven by the powder gases. Other operating principles for self-loading firearms include blow forward, gas operation, and recoil operation. Principle of operation. The blowback system is generally defined as an operating system in which energy to operate the firearm's various mechanisms and provide automation is derived from the movement of the spent cartridge case pushed out of the chamber by rapidly expanding powder gases. This rearward thrust, imparted against the breech, is a direct result of the expansion of propellant gases. Certain guns will use energy from blowback to perform the entire operating cycle. These are typically designs using relatively low pressure ammunition, while others will use a portion of the blowback to operate only certain parts of the cycle or simply use the blowback energy to enhance the operational energy from another system of automatic operation. What is common to all blowback systems is that the cartridge case must move under the direct action of the powder pressure. Therefore, any gun in which the bolt is not rigidly locked and permitted to move while there remains powder pressure in the chamber will undergo a degree of blowback action. The energy from the expansion of gases on firing appears in the form of kinetic energy transmitted to the bolt mechanism, which is controlled and used to operate the firearm's operation cycle. The extent to which blowback is employed largely depends on the manner used to control the movement of the bolt and the proportion of energy drawn from other systems of operation. How the movement of the bolt is controlled is where blowback systems differ. Blowback operation is most often divided into three categories, all using residual pressure to complete the cycle of operation: simple blowback, often just blowback, delayed/retarded blowback, and advanced primer ignition. Relating blowback to other types of automatic firearm operation, George M. Chin wrote that, in the larger sense, blowback might well be considered a special form of gas operation. This is reasonable because the cartridge case may be conceived of as a sort of piston driven by the powder gases. Actually, blowback involves so many special problems that it is best considered to be in a class by itself. The question whether or not it should be included within the more general class of gas operation or recoil operation is purely academic. The important point is that it partakes some of the properties of both classes and, depending on the particular problem at hand, may be considered to be either one. Simple blowback. The blowback, sometimes referred to as simple, straight, or pure blowback, system represents the most basic auto-loading operation type. In a blowback mechanism, the bolt rests against the rear of the barrel, but is not locked in place. At the point of ignition, expanding gases push the bullet forward through the barrel while at the same time pushing the case rearward against the bolt. The expanding gases push the bolt assembly to the rear, but the motion is slowed by the mass of the bolt, internal friction, and the force required to compress the action spring. The design must ensure that the delay is long enough that bullet exits the barrel before the cartridge case clears the chamber. The empty case is ejected as the bolt travels to the rear. The stored energy of the compressed action spring then drives the bolt forward, although not until the trigger is pulled if the weapon fires from an open bolt. A new cartridge is stripped from the magazine and chambered as the bolt returns to its in-battery position. The blowback system is practical for firearms using relatively low-power cartridges with lighter weight bullets. Higher power cartridges require heavier bolts to keep the breech from opening prematurely. At some point, the bolt becomes too heavy to be practical. For an extreme example, a 20 mm cannon using simple blowback and lubricated cartridges would need a 500-pound, 230 kg, bolt to keep the cartridge safely in the barrel during the first few milliseconds. Furthermore, the average force supplied by the return spring is limited to 60 pounds force, 270 N, or the bolt will not travel back far enough to feed a new round. Consequently, the return spring is not powerful enough to keep the bolt closed when the gun is tilted up. In addition, there is not enough energy stored in the bolt to cycle the weapon. Due to the required bolt weight, blowback designs in pistols are generally limited to calibers smaller than 9x19 mm parabellum, e.g., .25 ACP, .32 ACP, .380 ACP, 9x18 mm Makarov, etc. There are exceptions such as the simple blowback pistols from Hi-Point Firearms, which include models chambered in .45 ACP, .40 SNW, .380 ACP, and 9x19 mm parabellum. Simple blowback operation can also be found in small bore, such as .22 LR, semi-automatic rifles, carbines, and submachine guns, as well as in several low-velocity cannons and grenade launchers such as the Mk19 grenade launcher and Mk108. Most simple blowback rifles are chambered for the .22 long rifle cartridge. Popular examples include the Marlin Model 60 and the Ruger 10-20. Most blowback carbines and submachine guns are chambered for pistol cartridges such as the 9x19 mm parabellum, .40 SNW, and .45 ACP. Examples include the MP40, Sten and Uzi. There were also a few rifles that chambered cartridges specifically designed for blowback operation. Examples include the Winchester Model 1905, 1907, and 1910. The inertia needed to counteract the force of more powerful cartridges would result in inconveniently large blowback design firearms. For this reason, most modern semi-automatic handguns firing high-powered cartridges employ a short recoil system, with a locking barrel and slide assembly instead of a bolt. Advanced Primer Ignition, API, blowback. In the API blowback design, the primer is ignited when the bolt is still moving forward and before the cartridge is fully chambered. This requires a very careful design to ensure the proper balance and equalization of forces between the projectile weight, propellant charge, barrel length, bolt weight, and return spring strength. In a simple blowback design, the propellant gases have to overcome static inertia to accelerate the bolt rearwards to open the breech. In an API blowback, they first have to do the work of overcoming forward momentum to arrest the forward motion of the bolt. Because the forward and rearward speeds of the bolt tend to be approximately the same, the API blowback allows the weight of the bolt to be halved. Because the momentum of the two opposed bolt motions cancels out over time, the API blowback design results in reduced recoil. According to Anthony G. Williams, the API blowback principle is used virtually in all open bolt submachine guns. Technically, although generally these are known as simple blowback weapons due to the very late ignition of the cartridge compared to specially designed API blowback guns like the Mk108, although the relatively low pressures and velocities mean that extended chambers and rebaited rim cartridges are not required for submachine guns. In heavier weapons, Advanced Primer Ignition, API, was originally developed by Reinhold Becker for use on the Becker 20mm automatic cannon. It became a feature of a wide range of designs that can be traced back to Becker's, including the Oerlikon cannon widely used as anti-aircraft weapons during World War II. To increase performance of API blowback firearms, larger caliber API-B guns such as the Becker and Oerlikon use extended chambers, longer than is necessary to contain the round, and ammunition for API-B firearms come with straight-sided cartridges with rebaited rims. The rear of the cartridge case is smaller in diameter than the front. The last part of forward motion and the first part of the rearward motion of the case and bolt happen within the confines of this extended chamber. As long as the gas pressure in the barrel is high, the walls of the case remain supported and the breech sealed, although the case is sliding rearwards. This sliding motion of the case, while it is expanded by a high internal gas pressure, risks tearing it apart, and a common solution is to grease the ammunition to reduce the friction. The case needs to have a rebaited rim because the front end of the bolt will enter the chamber, and the extractor claw hooked over the rim therefore has to fit also within the diameter of the chamber. The case generally has very little neck, because this remains unsupported during the firing cycle and is generally deformed, a strongly necked case would be likely to split. The API blowback design permits the use of more powerful ammunition in a lighter gun than would be achieved by using simple blowback, and the reduction of felt recoil results in further weight savings. The original Becker cannon, firing 20 x 70 mmRb ammunition, was developed to be carried by World War I aircraft, and weighed only 30 kilograms. Oerlikon even produced an anti-tank rifle firing 20 x 110 mmRb ammunition using the API blowback operation, the SSG-36. On the other hand, because the design imposes a very close relationship between bolt mass, chamber length, spring strength, ammunition power, and rate of fire, in API guns high rate of fire and high muzzle velocity tend to be mutually exclusive. API blowback guns also have to fire from an open bolt, which is not conducive to accuracy and also prevents synchronized fire through an aircraft propeller arc. According to a United States Army Materiel Command engineering course from 1970, the advanced primer ignition gun is superior to the simple blowback because of its higher firing rate and lower recoil momentum. However, favorable performance depends on timing that must be precise. A slight delay in primer function, and the gun reverts to a simple blowback without the benefit of a massive bolt and stiffer driving spring to soften the recoil impact. The exacting requirements in design and construction of gun and ammunition reduce this type almost to the point of academic interest only. API mechanisms are very sensitive to the ammunition used. For example, when the Germans switched their MGFF, an Oerlikon FFF derivative, to their new, lighter Minengeschoss shell, they had to rebalance the spring strength and bolt weight of the gun, resulting in a new MGFF/M model with ammunition not being interchangeable between the two models. The 30mm Mk108 cannon was perhaps the apogee of API blowback technology during World War II. An example of API in submachine guns is the L2A3 Sterling submachine gun, where the maximum chamber pressure is achieved while the breech block is still moving forward and is about 0.46 mm away from the rear face of the chamber. The principle is also used in some automatic grenade launchers, for example in the US Mk19 grenade launcher or Russian AGS-30. Delayed blowback. For more powerful rounds or for a lighter operating mechanism, some system of delayed or retarded blowback is often used, requiring the bolt to overcome some initial resistance while not fully locked. Because of high pressures, rifle-caliber delayed blowback firearms, such as the FAMAS and G3, typically have fluted chambers to ease extraction. Below are various forms of delayed blowback actions. Roller delayed. Roller delayed blowback was first used in Mauser's Gerät 06H prototype. Roller delayed blowback operation differs from roller locked recoil operation as seen in the MG42 and gas operated roller locked, as seen in the Gerät 06. Unlike the MG42, in roller delayed blowback the barrel is fixed and does not recoil, and unlike the Gerät 06, roller delayed blowback systems lack a gas piston. This lack aids relatively light constructions. As the bolt head is driven rearward, rollers on the sides of the bolt are driven inward against a tapered bolt carrier extension. This forces the bolt carrier rearward at a much greater velocity and delays movement of the bolt head. The primary advantage of roller delayed blowback is the simplicity of the design compared to gas or recoil operation. The roller delayed blowback firearm action was patented by Mauser's Wilhelm Stahel and Ludwig Vorgrimler. Though appearing simple, its development during World War II was a hard technical and personal effort, as German engineering, mathematical and other scientists had to work together on a like-it-or-not basis led by Odt Helmut von Lossnitzer, the director of Mauser Werke's Weapons Research Institute and Weapons Development Group. Experiments showed roller-delayed blowback firearms exhibited bolt bounce as the bolt opened at an extreme velocity of approximately 20 m/s during automatic fire. To counter bolt bounce, the perfect angle choice on the nose of the bolt head had to be found to significantly reduce the opening velocity of the bolt. The extremely high bolt carrier velocities problem was not solved by trial and error. Mathematician Dr. Karl Mayer provided analysis of the components, assemblies in the development project. In December 1943, Mayer came up with an equation that engineers used to change the angles in the receiver to 45 degrees and 27 degrees on the locking piece relative to the longitudinal axis, reducing the bolt bounce problem. With these angles, the geometrical transmission ratio of the bolt carrier to the bolt head became 3:1, so the rear bolt carrier was forced to move 3 times faster than the bolt head. The rearward forces on the bolt carrier and receiver were 2:1. The force and impulse transmitted to the receiver increases with the force and impulse transmitted to the bolt carrier. Making the bolt carrier heavier lessens the recoil velocity. For Mauser's STG-45M project, Mayer assumed a 120 grams bolt head and 360 grams bolt carrier, 1:3 ratio. The prototype STG-45M assault rifle had 18 longitudinal gas relief flutes cut in the chamber wall to assist the bloated cartridge casing from the chamber walls during extraction. Fluting the end of the chamber provides pressure equalization between the front outer surface of the cartridge case and its interior, and thus ensures extraction without tearing the case, making extraction easier and more reliable. In 1944, other German companies like Grossfuss, Rheinmetall, and Henkel showed interest in developing roller-delayed blowback small arms. Grossfuss worked on a roller-delayed blowback MG-45 general-purpose machine gun that also remained in the prototype stadium during World War II. After World War II, former Mauser technicians Ludwig Vorgrimler and Theodor Loeffler perfected the mechanism between 1946 and 1950 while working for the French small arms manufacturer Centre d'études et d'armement de Mulhouse, CEAM. In 1950, Ludwig Vorgrimler was recruited to work for Setme in Spain. The first full-scale production rifle to utilize roller delay was the Spanish Setme battle rifle, which was closely followed by the Swiss SIG SG-510 and the Setme Model B-based Heckler & Koch G3. The G3 bolt features an anti-bounce mechanism that prevents the bolt from bouncing off the barrel's breech surface. The G3's bolt head locking lever is a spring-loaded claw mounted on the bolt carrier that grabs the bolt head as the bolt carrier group goes into battery. The lever essentially ratchets into place with friction, providing enough resistance to being reopened that the bolt carrier does not rebound. Due to the relative low bolt thrust exhibited by pistol cartridges, the anti-bounce mechanism is omitted by Heckler & Koch on their roller-delayed blowback firearms chambered for pistols cartridges. Heckler & Koch's MP5 submachine gun is the most common weapon still in service worldwide using this system. The Heckler & Koch P9 semi-automatic pistol and Heckler & Koch HK21 general-purpose machine gun also use roller-delayed blowback. Lever-delayed. Lever-delayed blowback utilizes leverage to delay the opening of the breech. When the cartridge pushes against the bolt face, the lever moves the bolt carrier rearward at an accelerated rate relative to the light bolt. Leverage can be applied with a dedicated part or through inclined surfaces interacting with each other. This leverage significantly increases resistance and slows the movement of the lightweight bolt. John Peterson patented the first known design for a lever delay system. The mechanism was adapted by Hungarian arms designer Pál Király in the 1930s and used in the Danuvia 43M. Other weapons to use this system are the Hogue Avenger and Benelli B76 pistols, the Cristobal carbine, the TKB 517 and FAMAS assault rifles, the AVB 7.62 battle rifle, the FNAB 43 submachine gun, and the Sterling 7.62 and AA 52 machine guns. Gas delayed. Gas delayed blowback should not be confused with gas operation. The bolt is never locked, and so is pushed rearward by the expanding propellant gases, as in other blowback-based designs. However, propellant gases are vented from the barrel into a cylinder with a piston that delays the opening of the bolt. It was used by some World War II German designs for the 7.92 x 33 mm Kurz cartridge, including the Volkssturmgewehr rifle, with little effectiveness, and the Grossfuss-Sturmgewehr, with slightly more efficiency, and after the war by the Heckler & Koch P7, Walter CCP, Steyr GB and M77B pistols. Chamber ring delayed. When a cartridge is fired, the case expands to seal the sides of the chamber. This seal prevents high-pressure gas from escaping into the action of the gun. Because a conventional chamber is slightly oversized, an unfired cartridge will enter freely. In a chamber ring delayed firearm, the chamber is conventional in every respect except for a concave ring within the chamber wall. When the cartridge is fired, the case expands into this recessed ring and pushes the bolt face rearward. As the case moves to the rear, this ring constricts the expanded portion of the case. The energy required to squeeze the walls of the cartridge case slows the rearward travel of the case and slide, reducing their mass requirements. The first known use of the system was on the Fritz Mann pistol in 1920 and later on the high-standard Corp Model T3 experimental pistol developed by Odt Helmuth von Lossnitzer while working for High Standard. The SIG SG 510 rifle family incorporates a chamber ring near the shoulder which is used to avoid bolt bounce rather than a delay element. The Secomp pistol has a ring near the rear end of the chamber. Hesitation locked. John Pedersen's patented system incorporates a breech block independent of the slide or bolt carrier. When in battery, the breech block rests slightly forward of the locking shoulder located in the frame of the firearm. When the cartridge is fired, the cartridge case, bolt, and slide move together a short distance until the breech block strikes the locking shoulder and stops. The slide continues rearward with the momentum it acquired in the initial phase while the breech remains locked. This allows chamber pressure to drop to safe levels once the bullet departs the barrel. The continuing motion of the slide lifts the breech block from its recess and pulls it rearward, continuing the firing cycle. The Peterson Remington Model 51 pistol, SIG MKMO submachine gun and R51 pistol are the only production firearms to have used this design. Flywheel delayed. Flywheel delayed operates by the rotational inertia of two flywheels, which are driven by a rack and pinion arrangement on the bolt carrier. Vector delayed. Vector delayed blowback re-vectors linear forces down and away from the operator. Toggle delayed. In toggle delayed blowback firearms, the rearward motion of the breech block must overcome significant mechanical leverage. The bolt is hinged in the middle, stationary at the rear end and nearly straight at rest. As the breech moves back under blowback power, the hinge joint moves upward. The leverage disadvantage keeps the breech from opening until the bullet has left the barrel and pressures have dropped to a safe level. This mechanism was used on the Peterson rifle and Schwarzlos MGM.07/12 machine gun. Off-axis bolt travel. John Browning developed this simple method whereby the axis of bolt movement was not in line with that of the bore. The result was that a small rearward movement of the bolt in relation to the bore axis required a greater movement along the axis of bolt movement, essentially magnifying the resistance of the bolt without increasing its mass. The French Moss 38 submachine gun of 1938 utilizes a bolt whose path of recoil is at an angle to the barrel. The Jitomatic and Chris Vector use modified versions of this concept. Radial delayed. CMMG introduced the Mk45 guard rifle incorporating a radial delay in 2017. This system uses the rotation of the bolt head to accelerate the bolt carrier of an AR-15 pattern rifle. The bolt locking lugs are adapted to incorporate angles that rotate the bolt as it travels rearward under conventional blowback power. As the bolt rotates, it must accelerate the bolt carrier to the rear through an adapted cam-pin slot. This acceleration amplifies the effective mass of the bolt carrier, slowing the speed of the bolt head. This delay allows pressure to drop prior to extraction without the penalty of a heavier bolt carrier assembly. The system is similar to roller and lever delayed blowback in that it uses the mass of the bolt carrier moving at a faster rate than the bolt head to delay the action from opening. Screw delayed. First used on the Mannlicher Model 1893 rifle, the bolt and screw delayed blowback was delayed by angled interrupted threads delayed by a quarter twist to unlock. John T. Thompson designed an auto rifle that operated on a similar principle around 1920 and submitted it for trials with the U.S. Army. This rifle, submitted multiple times, competed unsuccessfully against the Peterson rifle and Garand primer-actuated rifle in early testing to replace the M1903 Springfield rifle. This operation is one of the most simple forms of delayed blowback, but unless the ammunition is lubricated or uses a fluted chamber, the recoil can be volatile, especially when using full-length rifle rounds. Rotation of the bolt should be at least 90 degrees to prevent ruptured cartridges. Another form of this operation was developed by Mikhail Kalashnikov, who later developed a prototype submachine gun in 1942 that operated by a screw-delayed blowback principle, which is also found on the Fox-Wasp carbine. A pair of telescoping screws delayed rearward movement of the operating parts during the firing cycle. This weapon was ultimately not selected for production. Other blowback systems. Floating chamber. David Marshall Williams, a noted designer for the U.S. Ordnance Office and later Winchester, developed a mechanism to allow firearms designed for full-sized cartridges to fire .22 caliber rimfire ammunition reliably. His system used a small piston that incorporates the chamber. When the cartridge is fired, the front of the floating chamber is thrust back by gas pressure impinging on the front of the chamber as in a traditional piston. This, added to the blowback energy imparted on the cartridge, pushes the bolt back with greater energy than either force alone. Often described as accelerated blowback, this amplifies the otherwise anemic recoil energy of the .22 rimfire cartridge. Williams designed a training version of the Browning machine gun and the Colt Service Ace .22 long rifle version of the M1911 using his system. The floating chamber is both a blowback and gas-operated mechanism. Primer-actuated. Primer-actuated firearms use the energy of primer setback to unlock and cycle the firearm. John Garand developed the system in an unsuccessful bid to replace the M1903 bolt-action rifle in the early 1920s. Garand's prototypes worked well with U.S. military .30-06 ammunition and uncrimped primers, but then the military changed from a fast-burning gunpowder to a progressive-burning improved military rifle, IMR, powder. The slower pressure rise made the primer-actuated prototypes unreliable, so Garand abandoned the design for a gas-operated rifle that became the M1 Garand. AAI Corporation used a primer piston in a rifle submitted for the SPIW competition. Other rifles to use this system were the Postnikov APT and Clark carbine as described in U.S. Patent 2,401,616. A similar system is used in the spotting rifles on the Law 80 and shoulder-launched multipurpose assault weapon use a 9mm, .308 Winchester-based cartridge with a .22 Hornet blank cartridge in place of the primer. Upon firing, the Hornet case sets back a short distance, unlocking the action. Case setback. The case cartridge itself has been used experimentally to actuate the action similar to Garand's primer actuation. Known prototypes using this method of operation include two 1936 rifle designs, one by Mikhail Mamontov and another by Makar Goryainov at TSKB-14, and a 1980s design by A.F. Bereshev. The Mamontov and Goryainov rifles are only partially automatic, only the bolt unlocking is powered by the gases pushing the cartridge back, while the rest of the cycle, ejection, reloading, is done manually as in a traditional bolt-action rifle. A major problem with using the case cartridge as piston is that its motion is much faster, about 1 millisecond, compared to tapping gas further down the bore through a piston about 5 milliseconds in the Dragunov sniper rifle, which used the same cartridge as Mamontov's rifle. Bereshev made a fully automatic, but rather bulky mechanism that used a mechanical delay. In his system, the case cartridge pushed back a tilting bolt face, that upon reaching a certain angle pushes backwards an unlocking lever that continues farther before unlocking the bolt. The Grau however still gave a negative evaluation of Bereshev's gun, pointing out that the main problems with reliability of firearms using the cartridge case as a piston were known since the 1930s and still unsolved. Limited utility designs. Blish lock. The Blish lock is a breech locking mechanism designed by John Bell Blish based upon his observation that under extreme pressures, certain dissimilar metals will resist movement with a force greater than normal friction laws would predict. In modern engineering terminology, it is called static friction, or stiction. His locking mechanism was used in the Thompson submachine gun, auto rifle, and auto carbine designs. This dubious principle was later eliminated as redundant in the .45 caliber submachine gun. Lubrication or fouling would completely defeat any delay. Whatever actual advantage a clean, unlubricated Blish system could impart could also be attained by adding a mere ounce of mass to the bolt. Savage rotating barrel. The Savage system employed the theory that the rifling in the barrel caused a rotational force that would hold the gun locked until the projectile left the barrel. It was later discovered that the bullet had left the barrel long before any locking could occur. Savage pistols were in fact operating as simple blowback firearms. The French Mab Pa 15 and Pa 8 9mm pistols feature a similar design. Other auto-loading systems. Other auto-loading systems are blow forward, where the barrel is the only moving component of the weapon that is dragged forward by the friction of the bullet until it leaves the barrel. Recoil operation uses the rearward movement of parts of the weapon counter to the ejecta, bullet and propellant, moving forward, as described by Newton's third law of motion. Gas-operated reloading.
Please subscribe and thanks for watching.